We aren't just talking about cloning voices here, folks. We are looking at a system that orchestrates entirely new breathing acoustic realities from the ground up.
So this question really gets to the absolute heart of what researchers call the audio generation challenge. Because, while cloning an existing voice from a recording is one thing, acting as a director to design a brand new character's voice, direct how they perform a line, and simultaneously build a rich, breathing environment entirely from scratch, that is incredibly difficult. Historically, systems have totally struggled to juggle all these different audio elements at once.
Traditionally, we've dealt with this massive gap between two completely separate approaches. On one hand, you have zero-shot text-to-speech. It's kind of like hiring an actor and just giving them a reference tape. It perfectly clones a voice using a short audio clip. Instruct TTS, on the other hand, is much more like writing a detailed scene description for a director using natural language prompts. The problem? Current models usually struggle to do both of these well at the same time. If they're great at following instructions to build a soundscape, they usually lose that precise zero-shot voice cloning ability. Well, SwanTale bridges this exact gap.
Core achievements. What the researchers actually pulled off here is building a unified model capable of both zero-shot and instruct tasks, generating multi-speaker speech and audio in a single waveform. And to do this, they backed it with a massive custom data pipeline called SwanData-Caption. We're talking about a staggering 70 million annotated records. They even went ahead and generated targeted synthetic data just to cover rare scenarios. Things like elderly speech or incredibly hard to pronounce words. Alongside that mountain of data, they built three core architectural pillars: the SwanVAE autoencoder, a unified mixture of experts transformer, and a highly specialized training curriculum.
Let's map out how this entire methodology flows together. The process kicks off with the SwanVAE, which encodes raw audio into a continuous latent space. Then, a non-causal flow-based transformer sits in the middle and learns to map different conditions, things like text and natural language captions, onto those trajectories. And finally, there's a Unified MoE sitting right inside that transformer to handle the really heavy lifting. Let's break these components down, starting with the VAE.
Section 2. SwanVAE Compression and Alignment. So SwanVAE is a high-fidelity 48 kHz mono audio autoencoder. Its main job is to perfectly balance reconstruction fidelity, basically making sure the audio sounds flawless with compactness. It pulls this off by taking dense, high-res audio and compressing it all the way down to a 25 Hz latent sequence. To put it simply, it's taking massive, heavy audio files and perfectly ziplining them down into a tiny, manageable format without losing literally any of the HD quality. The encoder uses an architecture restricted to a local receptive field of just 0.95 seconds. And if you're wondering why, it's because it lets the VA totally obsess over the tiny acoustic details, leaving the big picture stuff to the downstream transformer.
Now, to successfully train this encoder, the system has to balance two major forces. On one side, you have dense reconstruction objectives. These use tools like SDFT and MEL loss, which is honestly just a highly technical way of saying they strictly constrain the fine, high-frequency details to keep the audio incredibly crisp. On the flip side, we have latent alignment objectives. These apply auxiliary guidance, things like generative flow matching and causal predictors, to ensure the latent space is actually diffusible. Essentially, it just makes sure the audio representation is mathematically easy for the flow model to learn later on, totally reducing unnecessary temporal redundancy.
This complex, highly balanced training approach ultimately guarantees that the reconstructed waveform retains strict semantic and acoustic structure. When the VAE decoder eventually projects those latents back into 40 millisecond waveform patches, the result is that pristine, flawless, continuous audio that ultimately reaches your ears.
Moving right along to Section 3, the flow-based brain.
At the very core of this brain is a non-causal diffusion transformer, or a DIT, trained with flow matching. This backbone maps all our inputs to that latent audio trajectory. It leverages a Quen family text encoder for actually understanding those complex director-like captions, plus a cozy voice tokenizer for the spoken words themselves. But here is the really genius part: Engram memory conditioning. Think about reading a script. If you see the phrase energetic girl or train whistle multiple times, you naturally recognize the pattern, right? Well, the Engram layer acts as a memory bank to quickly recognize these fixed caption patterns, which severely reduces the burden on the model's overall attention mechanisms. They also throw in reward condition quality control, basically forcing the model to bias its generation toward only the highest possible audio quality. But that raises a big question. How on earth does this system handle the sheer complexity of mixing speech, music, and sound effects all at once without jumbling them into a mess?
That brings us to Part 4, Unified MoE.
To keep the model from just collapsing under all this multi-audio-modality complexity, SwanTale leverages a mixture of experts, or MoE architecture, right inside the transformer. Normally, if you try to process smooth environmental sounds, transient audio effects, and complex speech all together, they just fight for the exact same neural weights. MoE completely prevents this traffic jam by dynamically routing inputs to specialized subnetworks. Think of it like hiring a dedicated Foley artist for your sound effects and a dedicated vocal coach for the speech, rather than forcing one stressed-out person to do absolutely everything.
SwanTale uses a highly specialized dual routing twist on this concept. The task router selects experts at a broad sample level, which gives stability to zero-shot versus instruct tasks. Meanwhile, the audio router uses frame-level routing to perfectly handle sudden transient events, things like a glass shattering or a very quick speaker change. They even include what they call null experts. These act as skip paths for near-silent regions, saving a ton of valuable computation. So the big takeaway here is that SwanTale allocates its brainpower dynamically and efficiently through a time-aware budget. Which finally brings us to how this massive architecture was actually taught to behave. Section 5. Progressive Training and GRPO.
The secret sauce here is curriculum learning. We can see a very careful four-stage progression. You can't just throw complex environmental prompts at a model before it even knows how to speak. So stage 1 builds a stable speech prior using just text and reference audio. Stage 2 introduces natural language for simple attributes like age and gender. Stage 3 brings in the full unified MoE and complex environments. And finally, Stage 4 applies high-quality supervised fine-tuning. This step-by-step process ensures the foundational skills remain rock solid as new complexities are carefully layered on top.
To put the final polish on this whole thing, the model undergoes reward-guided post-training using Group Relative Policy Optimization, or GRPO for short. This step acts like a microscope, fixing tiny recurring errors in pronunciation and attribute control. It uses a targeted reward suite evaluating phoneme accuracy and punctuation-aware pauses entirely without needing a separate value model. But here's the absolute most fascinating part of this stage: capability preservation through anchor replay. When you highly specialize a model to fix tiny speech errors, it can sometimes catch amnesia and literally forget how to generate music or environments altogether. By constantly replaying the original multi-speaker and audio data during this phase, SwanTale retains all its broad, world-building capabilities while achieving that pinpoint speech accuracy.
By elegantly solving both the data scarcity issue, thanks to that massive SwanData-Caption pipeline, and the crazy multi-audio-modality complexity challenge through its unified MoE and SwanVAE structures, SwanTale is just a massive leap forward. With the ability to simultaneously clone voices and conjure up breathing, cinematic soundscapes from mere text, how will this unified audio generation completely revolutionize the way we create media tomorrow?